We are live.
Careful with the back binding on it.
Oh yeah, I'm gonna do this.
Mine just literally just fell apart. Physicality? I think the book is back together again, but I had to use physicality.
Fake word.
Fake word.
Fake word.
I just don't have that. I can
But I suppose it could be a word.
I would look that up and see if it gets over 10,000 hits.
Yeah.
I think that for something like this, I would use a low threshold. I usually say, hey, look, it's got over 1 million hits in Google. It's a word.
Yeah. It could be a word.
No.
That's why I put it with the question.
Yeah, it's I don't know if Webster's agreed to this quite yet.
Webster's no longer matters. It's Google.
No, it's me.
They actually have a word possible.
It's like truthiness.
Well, Daniel Webster's the deprecated.
Integer 1 and
Yeah, exactly.
We could have whimsiness.
He may have looked it up. That's the thing.
Since all three students are women.
My mic is on.
You are on.
My mic is on. I have audio.
No swearing.
That's good. I know Webster's any good.
Yep, it's a word. Crap. It's in the thesaurus.
Don't say crap.
When I was 11 years old, I found a thesaurus. I looked up fool, and I could not stop laughing. And the points, the synonyms for fool were just hilarious to an 11-year-old.
Was it alphabetically organized or was it a Roget's?
It was Roger, and
Ooh.
it was topically
High five.
Yeah, well, I don't do a high five, but all right.
All right. Well, you know, it's one of these things that if you try to explain to some millennial what a thesaurus is, it's like he's confused. Is that like a rhyming dictionary?
We got caught on a couple of yours.
Oh yeah, I like it. You can make a small little thing.
Well, we're just
On some of your presentations.
we were just demonetized. We weren't booted off. They didn't delete them.
No, they just added ads. Yes, they monetized.
They remonetized it.
They
Yes.
remonetized it.
So,
We've got 3 of them that, yeah, they've got your music. The music. The music in the presentation.
Yeah, it's not the music so much as the performance, because the music is in the public domain.
No, not these presentations. Not the recording is not in the public domain.
Yeah, the performance is
Right.
this orchestra, the Berlin Verst Orchestra playing sausage and violin for...
But we got 3 of them.
All right. So I'd like to say that the stream is live, the audio is good, and everything's happy.
Everybody's happy.
2-minute warning. Coming soon.
So you're consuming, it's just that you're consuming from one end and attaching it to it.
Joe O'Connor, if you're out there, your talk is near. In an hour's away sense.
Depends on what copyright thing you want to
So, Andreas, were you planning on sitting down and being quiet before the actual start, or Why? What'd you do?
What? I don't know if I can do that to remove the audio.
I don't care if they throw some cats in it. I'd rather have your talk than.
So your radio wristwatch sometimes loses track of NIST in this benighted province. We're so far away from Fort Collins, Colorado, that the radio signal only reaches us in good radio weather. Only in Hawaii, as far as I know. But my watch won't pick up Hawaii.
Really? It shouldn't need to be synced more than once a day.
Well, it doesn't see good weather in these days. You know, some parts of the year it works really well, and I'm constantly in the black, and sometimes I just lose sync. So we're going to go by the Microsoft Windows clock in the lower right-hand corner.
What about WWVB?
My watch doesn't know about VAVB. You know, how many of us, for time and frequency, had to tune a shortwave radio? Okay, there's like 6 or 7. Wow. I had another silly ask, how many of you knew about X or Y question, and now I've lost track of it. So, welcome to the Silicon Valley 4th Interest Group February meeting, afternoon session. And I recommend the morning to you. It was jolly nice, and the audio may have been a little iffy for the remote talk for much of it, but you know, get over it. It's this dancing bear effect. It's not so much how well or badly the bear dances, it's just that he's there at all. This is the misspelled rumors, gossip, slander, libel, introductions session. Short and brief. I have one quick one. This is the Mount Almaden Air Force Station radar antenna. This thing spun around. They left in 1980, and it took all of these years for the Open Space District to make a trail and allow people up there. And unfortunately, as you can see in this other picture, this is about as close as you can get, and from the relative sizes, you can tell that either I'm a giant or it's far away. There's a fence here, and they're having some problems with asbestos and peeling paint because apparently they weren't that excited, but they were excited about the prospect of awarding the contract of sealing this to somebody's cousin. And this is all supposition on my part. It has no actual correlation to real facts that you can look up on the internet. Yes, John.
Mount Almaden. Where is it with respect to
Mount Amanum.
Amanum?
Oh, that's a good question, and we'll talk about that at the break. So, moving forward, you can now walk up here or drive up relatively closely, 160 steps, I think it is, maybe 6 or 8 stories of building. But you go up these steps from the parking lot that's right near it, or you can walk, I think it's about 8 miles round trip, more or less, up a hill. And that may be a meeting alternative for some time in the future. It may be after they get this thing painted or whatever they're going to do with it to actually allow you to walk up to it and commune with it in person. Ting, I think you had your hand up.
Okay, the Makers Fair.
Yeah.
Okay, the Makers Fair application would end tomorrow. Okay, tomorrow will be the last day to submit the application for a booth. So I just want to.
Do they need anything more specific than we apply?
Well, you have to submit a booth application.
Yeah, okay, it must have content and not just, hey, me too.
Yeah.
And a check, I presume.
Now, beg your pardon?
And a check, I presume.
No, no check.
Only if you're accepted.
No check. You
No
just have to
filing.
submit the application for food. I think that for commercial purposes, you may have to pay.
Well, we're not going to sell anything except our souls.
Right. So we had several occasions in the past years. I remember 3 years we had booths there. But this year I would not be able to submit or manage this thing. So, if anybody really want to do it, you have 1 day. Okay.
It may be a good idea to talk to Ting at the break offline, because he'll offer you good advice about how to go about it, if nothing else.
It's a little more challenging lately. The last few years, they've been tougher on nonprofit free booths. I was on the board of the Digital Game Museum, and 1 year they wouldn't give us space at all for it. So you have to be a little more compelling to attract their attention.
The Digital Game Museum, is that still a thing?
Well, it's a thing in the sense that there's still an organization and the items are in a storage locker, but it's not a place you can go anymore.
Okay.
Unfortunately.
At one time, they were sort of open intermittently, make an appointment to see the collection. All right, rumors, gossip, announcements, slander, libel.
In the Stanford Daily yesterday, they had an article that talks about a fairly new course called CS 107E, and with the CS standing for computer science. So that's a course, and the E in 107E stands for embedded. And so it says the course is called Computer Systems from the Ground Up, and that students receive a small single-board computer on the first day of class and build their own hardware-software system by the end of the quarter. And apparently what they're using is C, and they mention some projects that they've done on page 7.
Is that real-time C?
They don't go into any other detail on that.
It's 1984 C, which is double plus good.
The class is taught in C programming language, and the students learn command line programming tools. Instead of using existing libraries with pre-written functions, the assignments involve students writing the libraries themselves. Then the students use their libraries to build different aspects of a computer, from the machine's clock to its keyboard. Let's see. The assignments are weekly, and they build on the prior week's assignments. They end up essentially building an Apple II, is what it says. Yeah. Past final projects include a bike lock breathalyzer that uses an alcohol sensor to control a bike lock, an audio visualizer that maps sounds into colorful graphics, and a glove that translates American Sign Language into letters, which was a project that a student did here at Stanford in the early 1980s. And that's all they say about that class, other than it's a small class of about 60 students. No, well, maybe not that many. It's a small class.
Briefly.
Put this to your shirt.
Since Donald Trump follows our webcast the way he follows the Savage Wiener, I want to suggest to him that he consider breaking off relations and getting our troops out of South Korea, because the President Moon has gone moonatic. And he's got the General Huzitz, who killed all those South Koreans back years ago in the boat, yada yada. Why don't you come to the Olympics? It'll be cool. So he's got people really angry at him. Anyway, yada yada.
considering that Einstein was alive when Truman signed off on adding operational capabilities to the idea of a central intelligence agency, he did not think this through. And the talk this morning in regard of things should be as simple as possible, but not so simple as they seem. We're paying for that now, and I don't see a way out right before there can be less time. So we're out of time.
Somebody should have explained to him that they were using intelligence in a different sense of the word.
Oh no, the original charter for the intelligence, they drafted on those cowboys drafted off the operational capabilities, and Truman, who also said, yeah, if you're a member of the Communist Party, you are an enemy of America. That's his bag. He was not a wise man. He was simple and rough. He was simple.
And 2018, the Kestrel. So my name is Sam Falvo, as you can tell here. And yes, we've lost video.
Over scandal?
And we're not updating. So let me switch. Hang on, sorry. While we're offline, if you want soda next month, bring soda next month. I'll bring coffee.
Do we? Yeah, I was going to say, do we still have?
Just using the wrong camera.
I think it's because
That'll teach him. He has too many cameras.
too many cameras at the moment. Stanford's net filter, CIA Trump back.
Oh, that's what caused it.
For the conspiracy theorists.
Here's Black Hawk. Set up all the cameras. Sometimes that doesn't work either.
She was doing customer support on the phone. And just imagine the amount of patience and equality in her soul to be able to take a phone call from some asshole who just wants to talk to a guy.
Okay, we're live.
And being the first customer service representative for a computer industry. Cool. All right. Sorry for the interruption there. We've had some difficult technicalities. So my name is Sam Falvo. As everyone has heard ad nauseum at this point, I am the person behind the Kestrel. This, with any luck, will be the last status update of the Kestrel 2DX that you will ever hear from me. Because I've got some good news. But before I get there, let me just remind people what the Kestrel 2 actually is. It is a completely open source computer design. Everything is under Mozilla Public License version 2. So it's just copyleft enough to make me happy without being so copyleft that it's poisonous to businesses. It is strongly inspired by the Jupyter Ace. So if you've ever had the opportunity of playing with the Jupyter Ace and you found it rather enjoyable, odds are likely you'll probably find the Kestrel 2 to be enjoyable as well. I know I've certainly had a lot of fun with it. I'll get to that in a bit. It is architecturally very different from a Jupyter Ace, however. It has a 64-bit processor, not an 8-bit. It is a RISC-V instruction set processor. Instead of being a character matrix screen with only 128 characters, it is a 640 by 200 bitmap display. It is equipped with 48 kilobytes of block RAM. It's actually what comes standard on the FPGA itself. I do not use any external RAM. The processor itself is clocked at 25 megahertz, but since on average it takes 4 clock cycles to complete an instruction, that translates to 6 million instructions per second, roughly. And of course it has one SD card slot, and it's literally the baseline SD protocol, so up to 2 gigabytes of storage space is supported. The environment that it is running right now is called DX4th. It's my own custom implementation of Forth. I wrote it after being inspired by Chuck Moore's Programming a Problem-Oriented Language. So this Forth is about as far from ANSI compliant as you can get. That's not strictly true. I actually have ported some software from ANSI Forth to it with relative ease. But yeah, there's a lot of missing functionality to it. Don't expect software to run out of the box. Basically, the nice thing about the Kestrel 2 at this point is I actually spend most of my time using or programming the Kestrel 2 on the Kestrel 2. I actually have not touched my workstation PC in over 2 weeks for the purposes of programming this device, which kind of leads me to consider a possible new law of computing, which basically says that on any average day, if you spend more time using the thing that you are trying to build than the tools used to build it, then you're probably finished with it. So I've got that kind of paraphrased up there. So yeah, I just took this today. This is a horribly dithered picture that I took on my mobile phone earlier this morning. Did some processing on it with GIMP and converted it into the bitmap format and loaded it onto block storage. So this is an actual bitmap loaded off of SD card. So this is the memory map, and I'll get to, don't worry about this trash down here for now, I'll get to that in a bit. But this is the memory map, which will help explain that future explanation. I have 16 kilobytes of BIOS, which is synthesized ROM. It is not actually flash ROM or anything like that. I have no idea how to program flash ROM on this board. It does not come up on the JTAG chain, so I'm really at a loss as to how to do it without first. Maybe I have to write a program for the Kestrel 2DX, flash it through that, and then bootstrap off of the flash at that point. Yes. I don't have that.
Okay, well, that's a tool that will let you write straight to the flash.
Okay, so the comment was that I could use the Digilent Adept utility, which I don't have because I'm actually running on Linux, unfortunately. But the person commented that you can actually program the flash directly through that without having to do an intermediate program on here. So yeah, so basically I've got synthesized ROM. I was originally going to shoot for 32K, but unfortunately I'm at close to 72% FPGA utilization right now, and almost all of that is the ROM. And it's also slowed the logic down substantially because it's all asynchronous logic, of course. So getting to the block RAM, we actually have, the FPGA itself actually has, I want to say 52 kilobytes of block RAM, but it's arranged in a certain configuration that makes it less convenient. Like I can't really use all of it as part of this memory map, unfortunately. But I can use 48 kilobytes of it in a more convenient manner, and that's what I'm doing here. I'll get to how that RAM is being used in a bit. I also have 2 I/O cores. I've got the general purpose input-output adapter, the GPIA, and the keyboard interface adapter, the KIA. And you can see that they actually use relatively little address space per se. So the ROM BIOS, some people probably took note of how I bootstrapped the system. This is basically what you do. The first command when you first turn on the machine is the letter I. And what that does is that initializes the SD card. Then you type L, the address that you want to load forth into memory, which is 14300 hex. The first sector to load, which is at 0, of course, and then the number of sectors, which in this case is 32 sectors or 20 hex. And once it's done, you type G and then the address, and you're off to the races. That's how you get into forth. That interface is called TIM. It's actually named after the machine language monitor used to bring up the Commodore PET. Terminal Input Monitor, it's called. And my specific variant is called TIM/V for it being the RISC-V equivalent. The BIOS itself otherwise contains a bunch of subroutines which are useful. Keyboard input, console output, and SD card I/O as well. Remembering that the screen is actually just a bitmap screen, having the console output utilities is awfully handy to offload that to ROM because pretty much every program that you're going to use uses that in some capacity. So IPL RAM is broken up into 3 chunks, each 16 kilobytes in size. The first 16K is the video frame buffer and the return stack. Now the video frame buffer is 16,000 bytes. So the remaining 384 bytes is being used as the return stack. There is obviously, as you can see by the noise down here, a problem with blowing out that stack, and it blows out quite frequently, as people know by watching this presentation. It turns out that I'm not the best fourth implementation author in the world, and it seems like I stuff an awful lot of things onto return stack somehow. Plus, it doesn't help that each item on the return stack is, of course, 8 bytes wide because it is a 64-bit fourth. And therefore, I only have 48 entries on the return stack, which is not a whole lot. But it's good to know that I'm not using all that much. Like it's only just down at the bottom that you see the corruption. Moving to the middle 16K, we've got BIOS private data that's private to BIOS that helps it bootstrap. the implementation of cold, a bunch of primitives, do var, do colon. Then we've got console I/O, picture numeric output. Boy, that was fun to write. Block I/O, and finally, the last thing that I implemented was the compiler and what nowadays is called the REPL, but outer interpreter is what is more commonly known in Forth community. And then finally, in the third block of 16K, we've got just empty space for user dictionary. I have 4 block buffers, and then I want to say I've got 512 bytes of data stack, I think, because I know it's actually bigger than a return stack. So one of my future goals is to literally swap the data in the return stacks in memory and see if that helps with the corruption issue. So this is going to be, once it loads, this is going to be the block diagram of how all the pieces fit together on the architecture. So basically, we've got the MGIA, which is your monochrome graphics interface adapter. You'll notice that it has no connection to the CPU bus. It actually has no CPU accessible registers. It's all hardwired, and it's all hard-coded. The reason for that is when I first started the Kestrel 2 years and years ago, I want to say 2010, thereabouts, that core was intended to be used for debugging purposes only. It was never intended to be the actual display interface. So it's pretty awesome that it's lasted this long in its current form. I have a multiplexer which allows it to access one of the 3 blocks. You actually select which one of the 3 blocks using the GPIA. I've got a couple of outputs that are used to select the currently active screen memory. Otherwise, the SD card and PS2 keyboard, they all go to their respective controllers. The GPIA for the SD card, and obviously the keyboard goes to the keyboard interface adapter. Meanwhile, the processor, which here is drawn as a single block, but in actuality it's more like 4 or 5 cooperating blocks that all kind of sit together. They all work over a 16-bit Wishbone B.3 bus interface. So it's not completely asynchronous, but it's not as hard synchronous as Wishbone B4. Some of the folks may remember me talking previously about my desire to move beyond B3 for the various benefits that it has. That will come with the Kestrel 3, but I'll get to that a little bit later. So lessons learned, I've got different sections for different things. With respect to the BIOS, the specific way that I invoke functionality from the BIOS, like a lot of people familiar with IBM PC will remember load a bunch of registers and then issue int 10H, for example, as a trap. Atari ST programmers will, of course, use the trap A line to invoke system services. I actually don't do that. Instead, what I do is I scan low memory for a table of function pointers that point into ROM, and then I use offsets from that address to actually call the subroutines directly. The reason I do it this way is kind of long and involved. I don't want to go into too much detail because it involves some assumptions that I made which turned out to be wrong. But long story short, it avoids the use of the eCall instruction, which I think is a good idea in general, because the part of the purpose of the BIOS is to load the actual operating system, and theoretically the OS should be what implements the handler for eCall. So I don't want to usurp the operating system for that. The other reason I did it this way is because I have ambitions of porting AmigaOS, or at least a portion of AmigaOS, specifically the exec library, to the RISC-V architecture. And this is basically how Amiga libraries are invoked. So getting some experience with this early was actually very helpful. The keyboard I/O functionality is very capable and very flexible, but it's also incredibly hard to use. because you have to keep track of shift state yourself, unfortunately. But it is quite flexible, and it is pulled, which means you can use it without the aid of interrupts, which is awfully nice. Regrettably, it is a bit larger than I expected. It is exactly 16 kilobytes for the TIM and for just SD card, really basic SD card, console output and keyboard input. There's no room for anything else. So yeah, and that's the BIOS. We've already discussed the issues with Flash. Actually, I've already gone through this, so I'm just going to skip that. That basically just talks about how to locate the BIOS entry points. SD card, in my estimation, not worth it. After all these years trying to get a reliable SD card driver working, I'm basically just gonna, with the Kestrel 3, I'm just gonna say, nah, I'm not gonna bother. Yes.
Isn't there any way you can just offload that as, like some extra PARM chip or something, to run that as your driver with the program in it, and then just access it through your BIOS?
So I'm just going to really summarize your question because that's kind of detailed. Is there any way to offload that? Yes, there is. So that's actually what I plan to do with the Kestrel 3. The Kestrel 3 is going to upgrade to a intelligent I/O model, kind of like the Commodore 64 and the Atari 8-bits system that they used. And hopefully, I'll get to this, I guess, more detail a little bit later when I get to the Kestrel 3 section, but hopefully it'll be a whole lot faster than the 4 kilobits per second that 4 kilobytes per second that I'm getting right now. Because remember, I'm bit banging this, right? There's no DMA or anything like that. But the big problem, actually, the problem that I have with the SD card is not that it's slow. It's actually quite comfortable to use, despite how slow it is. The problem that I have is that SD cards, well, first of all, the protocol is horribly inaccurate compared to the specification. Case in point, implementing write capability for Forth so that I can actually save blocks from within Forth and not have to, like, jump through hoops. After I write one sector, the SD card would go into this bizarre state where the only way to get out, I would have to reinitialize the card as though I pulled it out and plugged it back in. So I would actually have to spend 100 to 200 SPI clock cycles after every sector write in order to get this card to respond again. And right now, the program code is actually doing exactly that. So I'm a little sketched out by the lack of coherence in the SD card protocol specifications. And the other thing that I found out is that when you access or when you modify a block a certain number of times, it has to wear level, right? I fully expect this. I completely agree and understand, and I've signed the dotted line on the contract that basically says, yes, I accept that wear leveling has to happen. I did not expect it to take 30 seconds to 90 seconds. There's no reason for an SD card to take 30 to 90 seconds to wear level. It should have a map in its own memory space. I mean, these SD cards are fully functional ARM systems on their own. We know this. They're 32-bit processor cores with plenty of onboard RAM. It's got space for a table that says, okay, this sector has been erased so many times, now we have to migrate data or whatever. 30 to 90 seconds is unacceptable. Basically, if you've ever used a BASIC interpreter or a Lisp interpreter that was old school and stopped the world garbage collected, and your terminal froze, mouse freezes, everything freezes. It looks literally like the whole computer just deadlocks while it's sitting there garbage collecting. That's exactly what happens here. I was absolutely not happy about that at all. And even if it does need to take that long, I expected it to happen concurrently or in the background while I/O activity was not actually happening. Turns out that's not the case. I was very disappointed with SD card. Lessons learned with regards to DX4th. Oh my God, this is so much fun. I have been using the Kestrel 2 for development, for slides and stuff like that, and just dinking around, just playing around for probably the last 3 weeks now, as of giving this presentation. It is beautifully liberating to work with native blocks again. It feels like I'm using an orthogonally persistent operating system because I don't have to consciously think, oh, do I need to save this? Do I need to, how do I name this? Like all those thoughts just disappear. It is wonderful, incredibly liberating. But again, the return stack is too small. You may have noticed the garbage at the bottom of the screen. And I've tracked it down to this particular sequence. So anytime you type a command on the command line, evaluate handles it. If whatever you're evaluating executes a load, and then that in turn executes another load, it completely blows the stack because of the state that it has to save on the return stack for returning back to where it has to interpret from. So in the future, I think I'll probably come out with a revision of Forth that swaps the data and return stack. That should help. But we'll see. So for now, if you want to play around with the Kestrel 2, build it yourself. If you happen to have a Nexus 2 or whatever, you can, anytime you do anything with the screen, use or assume a 640 by 192 or smaller graphics area just to be safe. That way there, even with 640 by 192, that gives the stack an extra 80 cells to play with. And as you can see from the screen refresh rate, DX4th is incredibly slow. And it is mostly written in colon definitions, not in primitives, as you can imagine. It is a 64-bit Forth, but it does fit in 16K. So the way that I do it is kind of, I use a direct threaded Forth. The threaded tokens are 16 bits wide. And this is an implementation of next, except for the very first instruction. The first instruction is intended to represent the previous primitive. But when you add up the jump to next plus the implementation of next itself, with this particular processor, it runs in 19 cycles, which is more or less gives you 315,000 Forth instructions per second. This is theoretically perfect. This is all assuming null functionality. In reality, I measure 195,000 roughly Forth instructions per second. So roughly 2/3, right? So it's not too bad, but it sure as heck isn't a speed demon either. So where do we go from here? Do I keep working on the Kestrel 2 or do I keep working and move on with the Kestrel 3? And in thinking about it more, there may not be much of a difference between the two because by definition, the Kestrel 3 will build on top of what I've already built with the Kestrel 2. So in a way, it's kind of the same thing. Programmable interval timers, better IRQ support. Believe it or not, even though I don't actually use interrupts on the Kestrel 2, it does actually support them in hardware. And part of the reason it does that is because the processor that it's currently using was originally intended for the Kestrel 3, but I just never got far enough to actually use it in that capacity. So the Kestrel 2 does actually have interrupt capability. It just doesn't actually use it right now. Let's see here. The other thing is just to say, okay, the Kestrel 2 DX is done. Let's move on with the Kestrel 3 design. So that's kind of the possibility that I'm mulling over right now. But honestly, I'm probably going to take a month or two break from anything Kestrel 3 related, just so that I can have more fun with this, because I'm actually ecstatic with this. Okay, so before we move on to Kestrel 3 related stuff, is there any other questions so far? Yes?
Can you move your scan over a little bit so that's all on the screen? So
the question was, how do I adjust for the underscan on the side here, or the overscan rather? The answer is I don't. Unfortunately, I do not have an exact 25.152 megahertz dot clock. I have 25.000. The problem with that is LCD monitors like this can adjust for it perfectly. Projectors typically don't. I can't really do anything about that. That is actually the only, I mean, in terms of software, of course, I can always just adjust my program so that it just prints everything with an extra space over. But without knowing that this would have happened, there's no way for me to anticipate that.
Everybody's nodding, yeah.
Yes? I'm sorry?
Are you using Vibe to edit blocks?
I am not. Vibe is too slow for this architecture. Vibe was designed for a computer that ran at 450 megahertz, and I could afford to update the screen in real time with brute force approach. It would take a lot more smarts to be more intelligent to update this display. The last time I tried to port Vibe to the Kestrel 2 environment, it took something on the order of 3 seconds to update the screen after every character. It's doable, it's just that it's just slow. But Vibe will be coming soon, eventually. I will update it, because having to edit blocks at the command line is very inconvenient. Doable, but... Okay, so I'm going to start moving on to Kestrel 3 stuff, unless there's any more questions. All right, Kestrel 3. So one of the problems with the Kestrel 2 is it runs on a Digilent Nexus 2 FPGA board, and it can probably be ported relatively easy to other FPGA boards. However, these other FPGA boards, generally speaking, are not open source. So like an Altera DE1 will not, that's certainly not open source. The people that I talk to online are very supportive of the Kestrel project, but they really, really want me to port this to something that can run off the Yosis toolchain. And the problem is, Yosis at the present time doesn't understand anything from Xilinx or Altera. So I have to target smaller FPGAs, specifically the ones that Yosis targets, and that's what these are here, the ICE40 HX4K and the HX8K. The problem is, these devices, at least with respect to the Kestrel 2DX design, they are almost exactly half the size that I need. Which means in order to make good of this, I need to break the design up into 2 pieces. So that's what I'm proposing to do here. So the Kestrel 3 is probably going to require something on the order of 2 ICO board gammas, for example. Something that, and that's not even the cheapest configuration. There's also the MyStorm Black Ice that you could possibly use. But these boards are equipped with the open source capable FPGAs. And they will be communicating with each other over what I call a bytelink, but I'll get to that in a bit. But the nice thing about this, there's good sides and bad sides, right? So the cost is increased latency from unsynchronized clocks. What this basically means is, as slow as the screen update is here, it's going to be even slower, probably up to 40 times slower with the Kestrel 3, because I'll get to the technical details of that in a bit. Still fast enough for full screen animation if you treat it like an old school IBM VGA adapter running on an IBM XT. on an 8-bit port. As long as you do it that way, under those certain circumstances, it will be fast enough to be usable. If you don't use that, then it will actually slow down to a crawl. The upside of this is that the CPU can be scaled up. It could be, I'd come out with a better design for a CPU. Maybe I could swap it out for a 53020, which I haven't designed yet. Or I could swap it out for a Rocket Core, which is capable of running Linux, right? Or I could scale it out. Maybe I want to run 3 of my processors in a multi-core situation, right? Or I could do all 3. As far as the all 3 part, I forgot this line. It also means that the I/O capability can be swapped out for anything that happens to be register compatible. So if my particular I/O is not sufficient for your needs, say for example you want video with sprites, or you want some other audio capability or whatever, you could swap out my basic design for something else, and as long as it's register compatible, it should boot and run just fine. So linking these 2 boards together is going to be something I call bytelink. So the idea here is these boxes here represent FPGA boards. Doesn't matter which one. It could be the Black Ice, it could be ICO board, whatever. The idea is that bytelink itself is going to be 2 2x6 PMOD adapter ports. These are, like if you come up and take a look at this, I've got my SD card thing plugged into just one of these cables. It would take 2 of these to basically implement one of these bytelinks. And the idea is whenever the CPU makes a reference to local memory, it's fast. It's incredibly fast. It will probably resolve that within 1 or 2 clock cycles. The bytelink, on the other hand, as soon as the CPU makes that memory reference, there's a signal inside the CPU that basically says, okay, I have not yet received a response for this bus transaction, so it'll actually pause at that point. It'll wait for external hardware to catch up. That gives me the chance to take that bus transaction, serialize it over one of those links on the PMOD interface, and in the I/O logic, deserialize it as though the CPU were running on this board. So the idea is the CPU never sees that there's any I/O happening here at the bytelink. The only way to tell is to use a timer and actually time accesses to I/O space. But semantically, they're exactly equivalent. This actually has a secondary and rather nice side effect, because if this CPU is independent, that means I can use the Kestrel 2DX as it currently exists and bit bang that port, which allows me to develop the I/O logic independently from the CPU logic. That's nice. Having actual hardware interactive, you know how people say, oh yeah, Forth is great for hardware bring up? Well, that's it right there. That is the textbook example of that happening. So I'm actually really looking forward to that. So how does Tilelink? Oh, I should step back a little bit. Bytelink is an adaptation of what's called Tilelink. So let me talk about what Tilelink is first before going back, because earlier I'd said that I wanted to use Wishbone B4. The problem with Wishbone B4 is that it's a little bit more complicated to use for this particular application. Tilelink, which is an open source bus interface that is actually closer to ARM's AXI3 than it is anything else, is almost made for this application. Whereas Wishbone B4, you can get it to work that way, but it's there's a lot of legacy cruft to it when used in this particular manner. So I'm actually going to go through my hardware and strip out the wishbone specific logic and put in Tilelink instead, which will actually make my designs more modular and more portable anyway. So if someone wants to, say, swap out the bus interface for an actual ARM AXI interface, they could do that, for example. Or at least they could do it much more easily without having to deal with bus bridges and all that other stuff. So there's upsides to that. It is a message passing interconnect, just like the AXI bus is, right? So it actually, the full spec specifies your bus has 5 different channels, A, B, C, D, and E, very helpfully named. Each channel is responsible for transmitting a specific class of messages. I will only need A and D. B, C, and E are only used if you have cache coherence involved, which may happen in the future, but not right now. So the A channel is used for address setup. It's what initiates your bus transaction. It also indicates if it's a read or write operation, which byte lanes are used. And if it is a write operation, it also supplies the data lines as well. D channel is for the return response, right? So that involves the acknowledgements, and in the case of reads, it also involves the specific data that you're reading. Because this is a message passing interconnect, this is actually how the processor is able to more easily wait for this. Because as soon as it sends out the message on the address bus, it just sits and waits for a response on the D channel. If anyone's familiar with, say, the green arrays GA144, the equivalent semantics for this would be sending stuff out the I/O port and then immediately reading back on the I/O port, expecting a response back. And basically, because no response is returned yet, your core basically sleeps. That's essentially how this whole logic works. So as I indicated earlier, the goal is to connect over a 16-bit path using two 2x6 PMOD connectors. I chose this particular configuration because it is a nice sweet spot for performance versus how much I want to spend on random paraphernalia. Because you can order all the cables that you need through Digilent, for instance, and it's relatively inexpensive. But at the same time, I also don't want to deal with like large quantities of tiny bits that can get lost. I've got 3 cats, so I need to keep their welfare in mind as well. And believe me, they go through everything. So yeah, it's basically strictly master-slave at this point. So the CPU will always be the master interface. The I/O will always be the slave. It is trivially easy to add bus mastering to this particular interface by simply allowing the I/O card to send messages on its A channel as well. So either one would work. So bytelink is just a mapping of Tilelink. And each path consists of 6 signals. I've got 1 clock, 1 frame delimiter that tells where one frame ends and another begins, and 4 unidirectional data lines to carry the data over that. And a frame, by the way, is basically just one message. So the biggest application for bytelink with respect to Kestrel 3 is talking to video memory. Because configuring the video display is relatively rarely done, so it won't take much time. Updating the screen is going to be 99.9% of the traffic that goes over that path. So I wanted to make sure that I had adequate performance. So the way I do this is, I basically just took a book out of old school PC VGA programming, which is you never read from video memory. Just don't. Instead what you do is you keep a local cache of video memory on the CPU card, and then you just blast when you make changes to your your local video memory, and you're ready to flip it onto the screen. You just blast it using 64-bit writes over that link. And when you do that, what you'll find is that we get 117 frames per second capability for monochrome screen and 29 frame per second capability for a 16 color display. This is all assuming 640 by 480 resolution. So just by comparison, the screen that you're looking at now is 640 by 200. So this is actually, the screen would actually be more or less slightly over double the resolution of what you're currently seeing now. So despite the bottleneck, it's actually fast enough for the CPU or whatever to actually do full screen animation, but just barely. Comparing it to other production buses, the Commodore Amiga Zorro 2 bus maxes out practically at 5.3 megabytes per second, although theoretically it's capable of 7. And the ISA bus is 16 megabytes per second. Yeah, and I already went over that. So the actual video display itself is going to be a redesign of the MGIA. It's going to consist of 5 components: the video timing unit, the video frame fetch unit, line buffers, and the new things are going to be the color interpreter and the color lookup tables. So it's going to be involve a palette-based color lookup. Unfortunately, there is no blitter, but that should be fairly easy to tack on later on if it's needed. Most of these components will offer registers that are CPU adjustable, hence the configurable graphics interface adapter name. But basically, I'm just going to kind of breeze through this. Video timing unit allows you to select different dot clocks, as well as setting how long or the duration of a horizontal sync, as well as its periodicity, and similarly for vertical sync. This allows you to select your actual on-screen resolution as perceived by the monitor. This actually doesn't adjust for memory fetch or anything like that. It does, however, have a raster counter, and this allows you to interrupt the CPU when a raster reaches a certain line. That allows you to do things like changing colors or changing video resolutions mid-display. Video fetch unit is going to be responsible for actually just grabbing data from memory. It does not perform any color interpretation, does not perform any color expansion. It is completely ignorant of bit planes or how chunky the graphics is. Basically, every horizontal sync, it's configured to fetch from one of 2 pointers so many bytes of data. That's it. And basically, it just dumps it like a garbage truck into a landfill into the line buffers. That's basically what that does. On the other side of the line buffer, the color interpreter unit, which is basically your dot shifter in a sense, this is where the actual interpretation happens. Basically, you have 2 parameters. You can say that a pixel has N1 contiguous bits in it. So you can have 1-bit, 2-bit, 4-bit, 8-bit, for example, for 2, 4, 16, and 256 colors. And you can shift the pixels every N2 clock cycles. And this allows you to, for instance, say, okay, every 4 clock cycles, I want you to shift by 4 bits or something like that. That way there, it allows you to make a color depth and resolution trade-off. So for instance, if I manage to pull off 50 megahertz capability, I could actually display 1,280 pixels on a single line, but I could never display more than 4 colors without running out of memory bandwidth. By the same token, I could do 160 pixels, but that gives me the ability to have up to 256 colors. Right? So I can actually make these choices. And with the raster compare interrupt, I can actually mix and match these multiple bands on the screen. And then everyone knows what a color lookup table. Basically, it's whenever I say draw pixel 14, you look up the register 14, and it has the red, green, blue values in it. Probably the only thing that's really unique here is that I'm allocating 48-bit of space instead of 24 bits. but yeah, they're mostly going to be not implemented. And of course, the rest of this is pretty lock, stock, and barrel, whatever we already have with the Kestrel 2, although with some changes. So the Kestrel 2 has a keyboard interface adapter, as I mentioned earlier. The Kestrel 3 is going to get a refinement of this. The refinement being that it's going to have 2 GPIO bits that allows you to send commands back to the keyboard, so that when you hit caps lock, for example, the caps lock light actually lights up. Right now, there's no capacity to do that unless you use the GPIA for that purpose. The GPIA, the revision of the GPIA is going to change as well. Instead of having 16 dedicated inputs and 16 dedicated outputs, it's going to have a single 32-bit I/O register, and then following that in the memory space, it's going to have a data direction register. That way there, it allows you to select on a bit-by-bit basis which is input, which is output. Coming out of reset, of course, it will default to the original GPIA just so that legacy software can boot up. In addition, I also plan on having interval timers in the new GPIA as well. This will allow me to handle things like SD card timeouts. It'll handle preemption when I implement multitasking, for example, and still have one counter left over for anything that's application specific. In addition, the events that it counts, the events could be the system bus clock, or it could be, say, rising and falling edges on an I/O pin. So you can. So I'm definitely looking to implement that as well. Whether or not this will actually see the light of day depends on how many lookup tables in the FPGA I can devote to that. And of course, a serial interface adapter that should allow anywhere between 300 bits per second to 25 megabits per second. Yes? Yep. CPU enhancements. Basically, it's going to be backward compatible with what's currently running on the Kestrel 2, but it will have additional privilege levels. So you can do, for instance, page level protection, for instance. I'm just going to skip over the operating system aspect. I'm thinking of enhancing DX4 rather significantly, actually, for this. In part because I'd like to take more advantage of the CPU's native instruction throughput. I'm going to take the BSPL compiler and the lessons that I learned with that and apply that here. Basically, it's going to involve a 13-pass nano compiler, basically. And the idea is to take Forth code and actually emit reasonably good RISC-V code output from that. And then will it be Forth 2000X compliant? I have no idea. Probably not, but it shouldn't be too hard to make it so. And that's it. And I think I'm over, so if there are no questions. What's that?
We were digging around with the
yeah.
Dennis. We just told Dennis is my hero. This to the world. James works to get to the front of her rather than sit there.
Yes.
You are using basically software to do the stacks, is that right?
Yeah.
Would you consider doing hardware stacks?
So the question was, I'm using software to manage the stacks. Would I consider using hardware? I have considered it, but I passed on that opportunity, in part because I just wanted the simplest possible implementation of the processor. But it is doable. The RISC-V architecture is designed for handling custom instructions and stuff like that. So it's an opportunity. We'll see what happens in the future.
I think since you are designing the hardware, it is easy to include hardware stacks. The software can basically forget hardware stack if you use a fixed length or stack, and let it wrap around. You don't even have to initialize it or reset.
Mhm.
So I think if you have the hardware capability to do the stacking in hardware, that will cut down your clock cycles significantly.
Cool, thanks. All right, so I'm gonna pass over the. Oh, okay.
Hi, my name's James Bowman, and I'm going to be talking about two things that one thing led to another that I've been working on the last couple of months, and I'll take about equal time on them, so it's two talks for the price of one. First thing I wanted to do was program an embedded device, and this might not seem very groundbreaking, but I got a bit sick of the ways of doing it that already exist, and this is my little journey on how I programmed a microcontroller. And it all starts a long time ago, before computers became cheap and plentiful. So there we've got one of the very first commodity computers, the Apple II. And what is great about this computer is it doesn't have any outsides. You just get a computer. So if you're interested in getting a signal off the computer, you can just go get it. It's all there for you. There's nothing between. Now, I don't believe this was any great golden age because the computer itself wasn't very capable. But as far as obstacles to getting at the computer and, for example, getting access to a binary signal, that was pretty great. It's literally right there in front of you. It didn't even have a case. Time passed and people started printing stuff, which doesn't really have anything to do with us, except that when they plugged their printer in, they had to use a standard port, and this seemed like a good idea at the time, the 25-pin DIN port, which people soon realized gives you GPIOs. You can access the printer port from the computer. You can drive the lines up and down and sense them. And huge amounts of stuff was hooked up to computers, to PCs, through the printer port. It was a big thing. If today you are a CNC person, you're very interested in finding a PC with a printer port still, because that's the preferred way of driving CNC machines. It's like people have got little stashes of them so they can still drive their little CNC mills. So that was great. You can do things like this. This is an AVR programmer. An AVR is the tiny microcontroller used in Arduinos, for example. This is a really small one with 6 pins. All you do is connect those 6 pins up to 6 lines on the printer port. With a bit of software driving the lines directly, you can build a flash programmer for the AVR. The only parts required are the wire. It doesn't get any better than that. What does the software stack look like? Well, the programmer utility, back in the day, that was a DOS program which talked to the printer port and toggled some bits. So not much going on there. There was itself, the physical medium, and then there was the target. That's all that's going on in that story. So there's not a whole lot to go wrong. When it does go wrong, you can look at the lines and find out what went wrong. It's probably a wire fell out. That's very little opportunity for failure there. Well, time passed and people still wanted printers, and the way they decided to hook up printers to save money, because it dawned on them that metal is expensive, is to use a much cheaper connector and replace the metal with electronics, and hence we have the USB port, much cheaper for the printer manufacturers. For us, a bit of a disaster, because there's no longer any directly accessible GPIOs coming out of the computer. In fact, there aren't any at all. All you've got is the various ports and the keyboard things, because frankly, we're a tiny market, the sort of people who want digital signals. So this is what we do instead. We take the USB connector, we put it through something which converts USB to GPIO signals, and then we hook it up on the backside there, and that's how you flip a bit on the outside world. And this is the preferred method. This is what we all do all the time when we want to connect GPIOs up to our machines. Well, it's perfectly simple. You've got your programmer utility, which knows how to talk to the USB device. It talks to the operating system USB driver stack. Somewhere in that stack is the USB driver for that black chip there, which is supplied by the vendor. Then there's the physical transmit, the host side of the USB. Then there's the device, and between them I've omitted the USB cable, which people often believe is the source of their USB problems. I'm skeptical of that. Then you've got the USB device. That's inside that black chip there. Then you've got the actual microcontroller, which can toggle bits. A microcontroller is just a small computer, but what's different about it is it has GPIOs on the outside, and it can flip them. And then finally, you've got the target, which is what you connect onto that connector. That's where your Atmel chip goes, so now you can load its flash. That's still current. That's how we all do it today. That's what you're buying when you're buying a USB programmer. I'm going to make the outrageous claim that it's all a bit flaky. That if you have a classroom of people doing this, for example, out of 25 people, 3 of them will get it working first time, and by the end of the day, almost everybody will get it working. That's how flaky it is. Why doesn't it work very well? Well, here's one reason that I have found to be the case when building systems like this. Well, one reason is there's 7 layers. So there's 6 interfaces that have to be decided on, and people quite often make mistakes and things go wrong. But another is mark the nodes in that chain which have state in them, which are stateful. Well, the only one that actually doesn't have any state is the target device, because it's a microcontroller and it gets reset every time you try to load it. Everything else has
Everything else has masses of state. And when you unplug it and plug it back in again, or you reboot your computer, you're resetting the state in various parts of these nodes. So relaunch the programmer utility, that resets the state in there. Reboot the computer, resets those. Unplug and replug in the USB device. All of these things are state resets, so you can get the state back in sync, and the whole thing might have some chance of working.
People who brought their own computers. There's other stuff that you can't see that's not on the screen.
Oh yeah. Yeah. It's amazing. Let's rewind and remember that all this complexity was just to toggle some bits. A lot of these things are serial. So when you program a microcontroller these days, when you load its flash, it's all done through a carefully thought out serial interface that the manufacturer tells you about in the datasheet. Here, for example, is how you set a flash byte. You send a 1, 3 zeros, and then the byte. It couldn't be simpler. And incidentally, the sort of people who are victims to this sort of amazing complexity are the very sort of people who are very good at toggling bits and flipping bytes. They're embedded writers. But for some reason, we're all putting up with amazing amounts of stuff and buying it and using it and then complaining when it doesn't work. Wouldn't it be great if your computer, instead of having a bunch of USB ports hanging off the back, had GPIOs? Like it used to, like the original Apple, but was a fancy computer. So not like the original Apple in the sense that you could actually use it as your development machine. Is there such a computer where you can run the things that you need to do your work, and it's just your main computer, and has GPIOs? No, was the answer for a long time. But then mobile happened, and mobile CPU, mobile systems run Unix, which is sufficiently resource intensive to require a certain general purpose computing, and they also have GPIOs because they've got to run all the sensors in the phone. The thing is connected to the phone, and they're not going to be running a USB bus inside the phone, at least not yet. So it has all direct connections built into the CPU. So phone cores have these attributes, and inside here are all the mobile devices. But many of them are, you can't buy them. You can buy a phone, but you're not going to be able to get back to the shell prompt and actually use them, except for the Raspberry Pi and its ilk. So the Raspberry Pi came along. It's mobile technology. It's just mobile stuff repackaged. That's why the Raspberry Pi is so cheap and capable, because it's trickle-down technology from the mobile revolution. You get, current one is like a quad core running at 800 megahertz, but more importantly, it has all the GPIOs at the top. Here's this wonderful map of how they're all hooked up onto this thing, and you get more than a dozen of them. And they're not just GPIOs. They speak all sorts of protocols like I2C and SPI, all right there, all open source. Even better, Broadcom, the people who made the mobile chipset, sort of tell you how they all work. It's not secret. There's no weird reverse engineering going on. You can just read this book, which is on the Raspberry Pi website, and it tells you how to drive these peripherals. So you've got everything you need. So what you've got in the Raspberry Pi is a $30 device which you can compile, run all your development tools on, which also has these external connections. You don't need that USB nonsense anymore. All right, so I had all the pieces of the guidebook and a Raspberry Pi. All these peripherals are memory mapped. This document tells you a giant memory map of how to drive all the peripherals. So after I'd written this allow function, which did the necessary mmap to give you permission to access a piece of memory. All that then had to happen was just, that's the memory range we want access to, grant access to it, and then that's GPIO. That's the base address of all the GPIO registers. From then on, the GPIOs are accessible and you can mess with them from forth. For example, here's how you set an IO pin high. You write to this register here. So given a pin number, turn it into a bit mask here and write it to the set register. Similarly, to clear a register, to clear a GPIO, generate a mask and write it to the GPIO clear register. And that's all there is to it. It's memory mapped. So in those 4 lines of code, we've got pin access, and then this is just a little utility for testing things out, which given a pin number, drives it high and drives it low in an infinite loop until you press Control-C. How much does it suck? Because GPIOs are not that much use if they're really slow. Well, there's a picture from shaky picture from my scope last night. It's about 3.8 megahertz. So that's certainly quick enough to do interesting things. You know, some things are not possible at that speed. But it's certainly not going to be the bottleneck because we're driving it from forth. That's quite efficient on that side. And the sorts of things we want to do are writing flash, which just involves sending a command and waiting a lot. So the whole thing is looking really capable. There's one difficulty, and that is that we're running as part of a Unix system. And even though it's quad-core, you can lose time slices and miss stuff, so there's no guarantees. Unlike a little microcontroller, which has nothing better to do than to poll the GPIOs. This is a great big computer, and it can go away for microseconds on end. So you can't, for example, generate a timed pulse easily using GPIO access, because the CPU might steal away your process slot and then give it back to you maybe a millisecond later. So there's no timing guarantees on outputs. Yeah.
Are you running Linux?
I'm just running stock Raspbian, which is a Linux distribution.
Linux.
Yeah.
Okay. And you've written an application that goes out and toggles these.
I've written a G4 piece of code.
Okay, all right. So what I'm saying is, but it is an application program.
Yeah. Yeah.
In order to get around this problem, so I've had that same problem, you know, because Linux is not real time. You have to write.
Whoops.
That's going.
That's fine.
You have to write a kernel thread.
Stand next to the cluster so that the interwebs can hear it.
Yeah. Yeah.
Give that to me and I'll put it back together.
Right. Yes, there are real-time things for Linux.
Right.
And
What I'm talking about is instead of having an application which goes through is asking the kernel to do this stuff, because whenever you cross that kernel boundary, that's a mem copy.
Right.
That's software. So, but if you have a kernel thread running,
yeah.
then you're going to find this toggle free is going to be a lot higher.
I think I'm getting most of the CPU. It's just so I'm at 100% on my core.
Exactly. That's what I'm trying to say.
Yeah.
If you were to have this as which could be a loadable module,
right,
you will find that it'll be a lot faster.
Or
wait till I get G4 married to an RTOS and do the exact same thing.
So when I wanted to generate a timed pulse, I thought about the sort of real-time stuff, which I have worked on before because of the robot stuff.
Yes.
And then I came up with a brilliant solution, which was just to use the UART. If you send an ASCII 0 on the UART, you can actually adjust the UART timing to your convenience and then generate a single pulse. It works quite well. And that was actually just 5 lines of code, because that's all I ever wanted to do. I didn't really want to do full real-time stuff. I just needed to generate a timed pulse. So that's what I ended up doing, is I used the UART to generate the timed pulse. So that's a small thing, and I recommend anybody who wants to generate GPIO signals to give up on what they were doing before and just buy a cheap Raspberry Pi. Even if you burn it out, it's still cheaper than getting a programmer. So the thing actually works really well. And I've written forth bindings for the GPIOs, but the nice thing about the current Raspbian release is that the GPIOs are actually accessible from lots of different places, including shell script. So you can actually just write command line shell script to toggle the GPIOs. It's not very quick, but it's incredibly accessible. So they've got all of that problem solved. Okay, end of part 1. And bear with me.
Can you see these Bluetooth parallel ports?
Did you see my earlier diagram?
My USB isn't capable enough.
Yes, right. It works too well. Yeah.
The Raspberry Pi replaced the parallel port. Need for having a laptop with a parallel port.
For me, yeah, yes, but it wouldn't do for the CNC people, because they need strict timing. They've got.
They need a Wi-Fi parallel.
Right.
Oh, they're around. In fact, 10-base-T parallel ports have been around for 30 years, 20 years.
And if not, Raspberry Pis are Wi-Fi ready.
Yeah, because it just isn't painful enough.
So the microcontroller that I actually wanted to program is an EFM8, and I'll talk a little bit about it and what happened next with my little project. Okay, it costs not very much money. It's obviously one's time has to be factored into these things, but the EFM8 is so cheap you can use it anywhere, and when I buy them, I just buy them in 25s, because that's $10. It's you get a strip of 25 computers. Why not? The thing's tiny. That's a tiny footprint, so it's smaller than some resistors. It is very little. So a lot of the manufacturers make very low-end CPUs at about this price range. So everybody has something in the sort of around 30 cents. But the one from Silicon Labs, and they all have about the same resources. I think the microchip one is, it has 16 bytes of RAM. So be careful what you do with it. So this one has quite a lot of RAM, but actually much better is that it's a proper computer. The microchip one hardly has anything. It can just twiddle bits in a loop, and that's about it. But this one has a full set of stuff, including analog on every pin, and serial interfaces, which is a UART, SPI, and I2C, which is super simple to use because it's an 8-bit CPU. A whole bunch of power modes as well. So it's quite capable. It's not a crippled teaser device. You could actually use it to make something useful. And people do. It's automotive qualified. It's in a lot of stuff. But you'd have a hard time detecting it because it's so tiny. The other downside is that unlike more popular CPUs that people have heard of, it doesn't have a lot of tooling. In fact, the manufacturer's tool is the only one I could find. Here is the part I've talked about already, the programmer utility. On top of that, it's 8051 based, so it's still going the 8051. There's a C compiler, which on Ubuntu, on Linux, you run, it's a DOS program, but it's run under Wine.
I did some 8051 C compiler. There's it's called the
SDCC?
Yes, yeah.
Yeah, that's that is native. They're using their own one, so they're using a proprietary one, which is obviously much better. Yeah, and then you're using Eclipse, which they've used Java, Python, and Jython, and it's now so difficult to launch the application that there's a launcher to help you with the difficult process of launching it. And it took me, I wanted to use the Windows tool, so I used my Windows machine to install it. It took me 2 hours to install it on a speedy broadband connection and apply its patches. It installed all of its stuff, and it did actually do something surprising, which the whole thing actually did deliver the goods. I was able to run the Flash program on the target machine. There's something else they've got down there, which is that on the board is no longer just a simple connection. It's this giant block made by Sega, the embedded company. And that is, I counted this morning, I looked at it, it's 12 ICs. So I'm not sure what they're doing with 12 ICs, but part of, I think, these people's business plan is just to make it really complicated. I'm not sure if they've done that on purpose, but it's amazingly deep stack. How could you do anything? There's an enormous gap between the target, which the protocol it's speaking is trivial, and the stuff right at the top. So I didn't want any of that. The real reason I installed it on Windows was so I could snoop the protocol and snoop at this point and see how they were talking to their target device. Okay, what's the alternative? Well, a few years ago, Bob Nash and Charlie Shattuck wrote something called MyFourth as a kind of experiment. They'd been using Silicon Labs parts, I think, for their business, and they had their proprietary tool chain, and they wrote an open source GPL tool chain for the old Silicon Labs parts, which were a few years ago, about 6 years ago. And MyFourth, when I first looked at it, because it does come up in the Google searches for fourth on 8051, had a number of shortcomings. It was kind of crazy. It's an 8-bit fourth. So when you add 1 to 255, you get 0. It's, for me, this seemed ridiculous. Its standards compliance is that middle line there. That's probably as close as it gets to any kind of standard. Is if you've used ColorFourth or looked at it, you might kind of know what's going on. As a fourth, while you're looking at it, you're thinking, hey, this maps really well to the 8051. It's a fourth designed to fit the machine very closely. So there's no possibility of porting it to anything else. It's carefully tuned for the 8051. And then I rejected it on the basis of those 3 points. But over time, and having used it a bit, I've come around to their way of thinking that a fourth needn't be portable. If you're targeting a machine, a particular machine, and that machine is not very general, you'd better use a fourth that's optimized for that machine. And there's 2 ways of doing that. Build an optimizing compiler, which is really smart and uses a lot of pattern recognition to try to guess what you meant and emit a precise code which matches that machine. Let's hope it works. Let's hope that pattern matches. Or to just make it explicit and make a fourth which exactly matches the actual machine resources you've got underneath. So here's what a taster of what it's like to use their fourth. So here's type, as in type out a string, a counted string, implemented in AND's fourth. You've got to get the string length, do some stack manipulations, and then make a do loop. Then you can fetch the bytes, emitting them, and then incrementing the counter. In this fourth, in MyFourth, because it's ColorFourth family, there's an address register which holds the place that you're interested in memory. It's the best way to put it. So ColorFourth, in fourth we don't have any registers, in traditional fourth. color forth adds registers, and these are a kind of a pain because they're all hidden. On the other hand, for a register machine, suddenly things get a lot more efficient. So here we fetch a byte from memory and then start the for loop. Inside the loop, we fetch more bytes from memory and emit them. Each time the address register is behind the scenes being incremented, and you get a lot less code. Is it better or worse? Well, here's one aspect in that this code is fantastically inefficient. I was using Camelforth 8051 before. It generates enormous amounts of work to manipulate all these 16-bit values, all the stack shuffling. This is 15 bytes of 8051 assembly. I think I've got them right here if anybody's... Sorry? So they are quite daring when they designed my fourth. All fourths have looping constructs. Where do they keep the loop counter? It's normally very private. It's just done for you. Here you have to give a register number to use as the loop counter. So you're the janitor. Now, so pick a number and make sure they don't, if you're going to nest them, don't let them clash. And I thought this was a terrible idea at first, but then you can do things like reserve one for use in your interrupt routine. You can arrange disjoint sets of registers, and then you don't have to do any register shuffling. So all this low-level stuff is the price you pay. And you can actually see here, so this block, this is at plus, gets compiled into these 4 bytes. And then this is the beginning of 7 pound 4. Register 7 gets moved from the top of stack. And then down at the bottom here is this DJNZ is jumped back based on register 7 to the top of this loop. So the whole thing gets compiled into 15 bytes of direct assembler, and there's not much fat in there. Maybe if you are coding an assembler, you could save a couple of bytes, but it's really close to optimal assembler. So instead of paying a price of 4 or 5 times slower than assembler for writing in fourth, you're writing in a fourth-like, but getting really close. The whole thing, I've made a cheat sheet, just because it's quite hard to remember, has a whole bunch of words. One problem that a lot of embedded fourths have is that there are different kinds of RAM on embedded machines. This 8051 has 3 kinds. And in my fourth, they just have different access functions to read and write them. So P is for program memory, for flash fetching. So the P suffix on the address, on the memory accessors means fetch from program memory. So everything's explicit. Nothing's done for you. Arithmetic and logic very closely matches what an 8051 is good at. There are, for example, versions of some of the arithmetic operators which have an apostrophe on the end. That means use the carry flag. The carry flag is something that's explicitly under your control as a fourth programmer. Because it's a way of saving time. You don't have to mess around with if statements or things. You can use the carry flag just as you would if you were writing an assembly. You'll see these conditionals, some of them have a period on the end. That's because they work on single bit. So instead of just testing the value on top of stack, you can look at 1 bit and then do a conditional based on it. And that is also just 1 instruction on the 8051. So all of these things sort of expose 8051 stuff. So there's no real optimizer in the compiler. And that really is what turned me around. So if you're writing code for a general purpose machine, you're going to want to write in high level fourth and not think too much about the machine. I've got my x86 PC on my x64 PC on my desk and my ARM-based Raspberry Pi. I'll run G4 on both of them. I don't care about the machine details. It's plenty fast. But on a tiny machine, you're going to be writing a program which is custom made for that tiny machine. I am not going to be taking an XML parser and recompiling it for the EFM8. That would be ridiculous. On an EFM8, I'm going to do tiny stuff that moves bits around and has tight timing loops. So what's a good way to write EFM8 programs? Probably not in Ant's fourth. My fourth is a good way of doing it because the whole thing is going to be tuned up for this specific CPU. It's not just me who thinks this way. This is actually the vendor's development tool. By default, as you run your program, this is how you actually single step very slowly through your executable. It pops up the assembler on the other window. It's like equal space there of source code assembly language. But these people aren't dinosaurs. The reason is when you're coding for this tiny machine and you're writing stuff, you definitely need to know what the assembler's generated. You can't just write C code and forget about the assembly because the result would be a huge, slow disaster. So we're all playing the same game. When you're writing on a tiny machine, you better keep an eye on what it's doing and have a model of what the machine can do at the lowest level. Otherwise, you'll end up with terribly inefficient stuff. So we're all doing it. We're all looking at the assembly language. We all have to know that the 8051 has the carry flag or bit registers. With theirs, in the C compiler, it just tries to recognize patterns and exploit them. In my fourth, it's explicit. Here's a pleasing hack from last week. What I wanted was a version of key, that is, get a key from the console, but I was only interested in its least significant bit. And I wanted to take the key from the UART and then copy it onto a GPIO port, just for testing. So I wrote a new version of key, which calls the regular key. And then this is my fourth built-in. Divide by 2 and set the carry flag. And then drop it. And then discard the value because we don't want the top of stack anymore. So when this returns, the carry flag is taken from the least significant bit that came from the UART. How do you use it? Well, you call key, and then the carry flag is set. And this is a little bit of assembler to copy the carry flag onto one of the output ports. Job done. It's fourth, but with the carry flag. Well, it's not particularly portable if you're new to the 8051. But one thing to be said in its favor is the whole thing takes 4 bytes and runs in 4 clocks on the 8051. So in high-level fourth, it'd be some giant thing with if statements running in hundreds of clocks. Here, very tiny, tuned up for the machine. What's on my desk? Well, I'm running my fourth on the Raspberry Pi. I'm running the programmer utility also on the Raspberry Pi, all running under Raspberry Pi G4. It's all integrated. It talks to the GPIOs directly, and that's connected with wires up to the target. So getting quite close to that DOS version of development. And here it is. This, obviously, the previous slide was a platonic ideal, and this is the sad reality. There's a lot of wires involved. So this is the Raspberry Pi. These are the 2 debug wires which program the flash on the microcontroller, which is lost in this nest of wires here. And then the microcontroller's job is actually going to be to drive this graphics display, and this is fourth drawing all of this stuff. This is the actual application running, written in my fourth. So there's a bunch of SPI connections coming off the microcontroller here, and the rest is just power. So it all works. This is what that board will become. That's just a stopgap measure. There will one day be an actual finished version. One thing about my fourth is when they wrote it, they had to use a bootloader. So bootloader is yet another part of the stack which talks on USB or UART and then allows you to write flash. But more modern EFM8 parts actually just have a binary protocol for writing the flash. So there's actually no bootloader required. You can just toggle a couple of pins and rewrite its flash, and it can't do anything about it. This is good because their bootloader was 500 bytes and the whole thing only has 2,000 bytes. So it's a big saving to have no bootloader. They also had an interactive element in MyForth so that you can log in on the UART and type stuff in and make your microcontroller do stuff. I also got rid of that because when the compile run is so quick, I mean, it is just press a button and a fraction of a second later it's running. You don't really need an interactive forth, I find. If I want to run a particular command, I just type it in just after main and then run it, and then compile and run. It's almost the same as being interactive. There's no real need for interactivity when that time is very short, because you can just load a new program. You're not going to wear out the flash. I think it's 100,000 reflash cycles. So that's it. It's working very well. It's all happening in Forth. And next month I'll talk about the application that's actually running in MyForth. All right, that's all I got.
We're going to take a short break and have some birthday cake. Cool.
The only reason I'm looking at a more general purpose compiler is I tried doing a specialized
RISC-V?
or RISC-V.
Yeah.
It's just too generic. Yeah, my experience with machine forth
Right.
were just disastrous.
Oh.
Yeah, it was actually faster to use classical forth than it was to use machine forth.
Right.
Yes, that's why I ended up going the more conventional route.
Right. Yeah. Yes. Right. Well, that's the nice thing about this setup is I kind of understand every part of it. So you can shift it onto another. Yeah.
When I saw what that's why I saw it. Linux, and just look at your time.
Yeah. Good to get control of the machine. I mean, it's got a lot of CPU power.
Oh, God, yes. That's what I'm going to target. Is the Raspberry Pi.
Right, yeah.
Because I'm going to turn it into a USB hub.
Yeah.
But the difference between my USB hub and my other one, yeah.
Because it has 4 ports, right? It has 4 ports.
You mean
4 USB ports.
yes? Those would be
That's your connection.
the
Oh, sweet.
downstream.
Right.
That's why actually wants it. And then it's got a
Yes.
should have a
Micro USB.
micro B.
Yeah.
That you can plug in, and that's your one that goes up to the host.
Okay.
And with USB devices, you have more than one device in a USB device.
Right.
So not only can I make it
Right,
a hub,
yes.
but also I can literally have GeForce running in there that uses a terminal. I can fake that out.
Right.
That I think is
Yeah.
Plus, for debugging,
Yep.
I can have another port if I wanted.
Yeah. Yeah, it's interesting reading what they did. I thought it was terrible, and then hey, it's clever. It's very elegant. So he did 2. So this is 8051, and he did MyForth Arduino.
I think that's the one I saw. I think
Right.
he does it for his steno keyboards.
Yeah.
Oh yeah. That's so cool.
But then when you look at the code for his steno keyboards, it's like there's nothing there.
Oh yeah.
Yeah.
Yeah, it's all because if you know it's steno and stuff, it's all sound based.
Right.
You know, it's funny. I had a high school water polo coach had a brother that did that. The way my coach described his brother, I thought this guy is a genius on the level of Einstein. You know, the court reporter. The court reporters make a lot of money, you know, because of the talent. But but what Charlie did was actually, you know, turned it in and computerized it.
Right.
Oh, amazing.
The SID station is not something I knew about. I knew about the SID. The trade but I never heard of the SID station where someone built a box to use the SID as a synthesizer. So then there were stories about the kind of the batch of 100. The last ones were made in 2007. But there are various PGA or software or whatever implementations of this yeah, I had another half an hour or 45 minutes. Hey, Tim, how much would it cost for you to write a port for the IBM 1130? Small bills for 1130 stars. How about $100 and a t-shirt? $100? And a t-shirt. Think about it. Yeah, sure. Why not? Why not? Actually, it is already done several times. I just need to learn it. Okay, good. I've already decided FPC? And I'm not sure that yeah, well, there are software simulators you can use to figure it out. Yeah. And then at some point, it still works. I don't understand why you think you need to have PGA. Yeah, but I'm saying it's a software simulator for the instruction set. You can run it on your Windows.
Yeah, because I gave up.
We're just hoping for a forward.
I have no clue. Okay, I want to get over to, where am I? Oh, let's find it. What's that? I want to be over to here. Where's the mic? Where's the mic? And we are talking. Okay. What am I gonna do with this thing? Okay. Tab. Yes, we're going good. Okay. So I want to do a video call. Uh-oh. Well, what happened here? What happened here? Video output low. What? We lost the stream. Okay. One moment. And now we want to be over here.
There you are. Oh no, now we're back to this problem. I had this same thing this morning, and I've got to figure out what's going on. You're coming out my speakers, which I don't want. I want dead default. Yeah, that's better. And you might adjust your camera so that you're more into the picture. You're just at the bottom of your frame.
Is better?
Yeah, that's better.
Okay.
As long as we get a stream through here. Got to wait a bit for me to actually see the stream. The stream is actually very much delayed from what we do live. And